Robinson. Glad to have you with us here today for PHM Presents. An important topic and growing with importance as climate change accelerates, dealing with these oncoming heat waves and hotter temperatures. And, you know, how are we dealing with the PHPP and the cooling calculations to make sure that we're in a good place? So I'm excited to be here with Oliver Stile, who is a Passive House consultant and building certifier. I'll give a little bit more of an introduction in a minute. Before we launch into the presentation, as folks are coming in, I'll just say a few words about the Passive House Network. If you are not familiar, we're a 501c3 nonprofit. We're a nationally focused organization across the United States with membership in regional chapters. We encourage you to join and participate at that level. We have regular chapter meetings and discussions, networking online, virtually, so it's convenient and accessible. We're affiliated with the International Passive House Association and the Passive House Institute, and we work closely with the North American Certifiers Circle, which is a group of about 14 companies, over 30 individuals who are certifying to PHI's International Passive House Building Standards. And as I mentioned, Oliver is one of those certifiers. So our primary goal as a network is to connect people. The peer-to-peer knowledge sharing is really key in terms of growing capacity. That's what can scale. And in so doing, we are also focused on education in upskilling, and in particular, the Certified Passive House Designer course. We work with EMU Passive for the tradesperson course, and look towards certification as the ultimate educational tool. Going through those first building certifications is learning by doing and making sure that you are figuring it all out, if you will. So with that, I want to mention the Certified Passive House Designer courses are coming up. We have a hybrid regional course for the Midwest and the Mountain region, as well as for the South. We have a in-person training happening in Ventura County, I think, or Santa Barbara, in California, coming up at the end of the month. And later in the year, we'll be going to the Northeast and to the Pacific, the whole Pacific. And so you can sign up at any time, you get access to the platform and be on your way. It really, the Certified Passive House Designer course really changes one's vocabulary and how we think about buildings. The tradesperson course, we have upcoming courses. EMU does, Fort Collins, Colorado, in Vermont, in Minnesota, and more coming later in the year. Following on this conversation, and as a certifier, will be interesting, I think, today, speaking with Oliver, we're going to have another installment of Ask the Certifiers, and that will be with Raphael Wiebert from Hertz Lang, who's based out of Germany, but also certifies buildings in the United States. So I encourage you to join us later in June for that conversation. Immediately after that is International Passive House Days, Open Days, where buildings are open around the world. It's a global event, and there's really no better way to have someone learn about Passive House and get excited about Passive House. So we encourage you, if you have a Passive House or building a Passive House, to open it up to the public. And if you haven't visited one, it's a great opportunity. We will be listing more and more projects on our website, and also in combination with the International Passive House Association around the world. And finally, just to note to save the date again for our conference, which will be coming in the fall, September 28th online and in person, October 4th and 5th in Denver, Colorado. We'll have workshops, we'll have building tours. There's a lot of activity out there in Colorado. The program is about set to be announced. which we're really excited about. And tickets should be going on sale for early bird pricing in the next couple of weeks. So keep an eye out for that. Now, the topic at hand here today. PHM Presents, as you may be aware, is an ongoing reoccurring event that we have online covering a wide range of topics, diving into Passive House. And today we're really pleased to be looking at cooling, calculating cooling, and dealing with summertime heat wave issues and dealing with them successfully. Oliver Stile is CEO of Praxis Resilient Building, an engineering company based in Barcelona. So a lot of what we're going to be seeing here is in Spain and dealing with the hot climate in Spain. He's a certified consultant, a trainer, and a building certifier, active in the North American Certifiers Circle. He's a Master of Architecture, Engineering, and Environment from the University of East London. So without further ado, I'm pleased to hand it over to you, Oliver.
Fantastic. Thank you very much, Ken.
And I did forget. I said I wouldn't forget, or I would try not to forget. Please put your questions in the chat for the audience so we can have a good discussion here at the end. We'll be talking and want to feed in your questions as much as possible. There you go.
Fantastic. Thank you very much, Ken, and above all for the invitation today and for getting this organized and these great PHM Presents sessions, which I hope is going to be interesting for you all today. And thanks a lot for tuning in. It's always inspiring for us here in Spain. I mean, I'm English, Mexican, but live and work in Spain, in Catalonia, in the northeast of Spain. And there's happily lots going on here in Passive House, but it's always inspiring to see what's happening across the pond in the US and North America and US and Canada, because it seems like there's a really good impulse and lots of great projects coming online. Where did this presentation come from that I've put together today? Basically, it came from the fact that years ago, well, when we started working in Passive House, we were doing the Passive House consultancy for a project and the design of the mechanical services, including the cooling systems, and we installed them. And we used the PHPP modeling tool to size the cooling equipment. And then as the first summer kicked in and the heat waves started coming online, the phone started ringing, and the client was saying, "We're too hot, we have the cooling system on and it's not keeping us cool." So that was obviously not a pleasant experience. So I started to look into the sort of details of how PHPP calculates cooling loads in order to size cooling equipment. What I didn't know at the time, which I found out since then, was that there's a few things that are good to understand and to take note of if we're going to use it. If you're going to use it to size cooling equipment to deal with more extreme heat wave conditions. So yeah, as Ken said, and as we all know, everything's getting hotter. We can see that on this graph here, and despite 20-odd COP meetings, things just get hotter. So this is what we're going to be facing. Obviously, more extreme climate events all the time, but higher temperatures, and more sun. So we also have this backdrop, which has been particularly acute in Spain and in Europe, and I understand probably the same in North America, is increase in electricity prices. There've been a massive increase in the last 2 years. So that's obviously a big issue, and of course we need to avoid this. This image from Energy Vanguard is really kind of telling. We need to avoid having existing buildings just covered with air conditioning units, outdoor air conditioning units, strapped to the buildings to keep people, functioning inside, so we have a big job to do, obviously, in existing buildings, and we've got to make sure that every new building is done properly, so that we're using as little active cooling as possible. Okay. And of course, there's also this, this graph here shows a prediction of the IEA of the world's households that could have an air conditioner over the next 20, 30 years, so an absolutely massive increase predicted in terms of how many people are going to be buying air conditioning units. So, that's significant, because it's going to create a huge stress on the electricity grids, because even if the number of cooling hours is less than heating hours in some climates, the fact that everybody turns air conditioning units on at the same time is going to cause a lot of peak demand issues, so we, obviously we need to really address this, and passive house, of course, as we all know, comes from a relatively cool temperate climate in its origins in Germany, but it's been expanding rapidly across the world. So adapting, exploring all of these issues in terms of active cooling is going to be and is super important. So a few sort of tips, recommendations, and reflections that we've learned along the way of the last 12 odd years of working in passive house in warm climates, particularly warm, humid climates, coastal climates, which are the most tricky. Always we've got to start by maximizing passive cooling strategies. So we're talking good insulation on roofs. We're talking shading of openings, above all, natural night ventilation with thermal inertia if nighttime temperatures are low enough, cool colors, radiant barriers, radiance, roof buildups, and a series of other ones. So the first step, even if we're going to use active cooling, of course, should always be to optimize the envelope, to bring down those cooling loads as far as possible, so that we can then use the lowest power cooling equipment to keep people happy and comfortable inside. And then, of course, the second step is, size that kit correctly, because passive house buildings are different to conventional buildings. So the rule of thumb that an installer or an engineer may apply to a passive house building is not going to be appropriate. It's going to be oversized, So we need to size the cooling equipment correctly, and we need to obviously distribute that throughout the building. So we need to get heat out of the building equally in all the different spaces, take into account different orientations and heat gains and occupancy gains and so on, So if we oversize cooling equipment, and of course there's going to be unnecessary initial capital costs to the build, and of course it's going to be higher running costs. So the energy bills are going to be higher, because the cooling equipment is even if it's running at its lowest possible power, it's still going to use more energy than if it was sized adequately, So we need to watch oversizing. We need to watch undersizing, of course, too, because otherwise there's comfort problems, and that's where, the story of our clients who rang us up after everything was installed in the first summer was an issue. It was undersized, so we need to avoid that. And obviously, we need to deal with overheating, peak loads, heat wave conditions, and particularly in humid climates, high humidity, So clearly, in a passive house building where you have a really good thermal envelope, which keeps heat in the winter, it's logical that in the summer, any heat that gets in there is going to dissipate more slowly, because that's the objective. That's what we're trying to do in the winter. So, obviously, a passive house building can be susceptible to overheating if we're not on top of, first of all the passive cooling strategies, and then a cooling system that can deal with short-term peaks, given all of these increasing heat waves. So the bottom line is we want to deliver comfort in the summer at super low energy. That's where we want to go. Whether or not we're certifying a building to passive house standard or not, that should be the objective. So the certification has obviously a whole lot of criteria that we need to meet, but we also need to take into account other issues like, preferences, user preferences, talk to our clients, see what they want in terms of comfort in the summer. So the question is, we've put all this work into getting a PHPP energy model up and running, the passive house planning tool, the energy simulation package that we use for passive house. So we've put all this energy into getting the tool up and running, but can we use it to size cooling kit? Yes, of course we can. We can use anything. We could use an Excel spreadsheet. We could use a expensive thermodynamic multi-zone model program too. There's a whole lot of things that we can use. But the gist of this presentation is, if we're going to use our PHPP model that we have up and running for a certification, can we use it to size coolant kit, and what are the things that we need to look out for? So just quickly, some of the summer comfort parameters that the PHPP and the passive house certification, PHI certification standard is looking for. This is this is a sweet spot where we want to be in the summer. And of course, these are centigrade values. So 22 to 25 degrees, operative temperature is 72 to 77 degrees Fahrenheit. Okay, so this is where our PHPP is calculating the sweet spot that we want to be in. Okay, with an absolute humidity of 12 grams per kilo. Okay, so that's equivalent to 25 degrees centigrade operative temperature at 60% relative humidity. Okay, so that would be 77 degrees Fahrenheit, 60% relative humidity. So talking to Ken earlier, I'm aware that in the US, some preferences may be to have lower temperatures than that, but that's where we need to talk to, you need to talk to the client and establish a little bit what the expectations are going to be. But this is where the PHPP is trying to get us to. Okay, 22 degrees being the minimum temperature, because if you, in the summer, you have left clothes, your clothing level is less. So below 22, you might start to feel a bit chilly. So that's where the 22 comes from. Obviously, in the winter, we're down to 20, no? So this is where we're looking to be with the compliance with the passive house standard. And this is a graph that shows how not to do it. This is some of our experience in these kind of projects where we early projects, and the one I was mentioning, where we use the PHPP cooling loads just as they came off the PHPP for the certification. And here what you can see is monitored data in the main bedroom in a heat wave here in July 2019, looking at air temperature and relative humidity. So this isn't operative temperature, because operative temperature is quite difficult to measure. It's the average of the air and mean radiant temperature. But what we can see here clearly is that people are getting too hot here. It's getting up to 29 degrees, humidity not too high, but obviously these are temperatures even way out of the extended comfort range, which is debatable whether people are comfortable at 27.5 degrees centigrade at 40% relative humidity. Okay, so this is what we want to avoid. Another example, in a more humid climate, where you can see that the humidities are higher and the temperatures are high too. So the issue of getting cooling kit size properly is clear in these examples here. In our experience, high humidity and high temperatures is a problem. In fact, humidity is often more of a problem than higher temperatures for a lot of people. You're not able to sweat, to transpire, to dissipate as much heat from your body, and it becomes extremely uncomfortable. You might be okay at 27 degrees at 30% relative humidity, but once you get up to 60, 70% relative humidity, you really start to feel uncomfortable. What we did in those two examples that you've shown, the one that I mentioned, was just the classic cooling coil and the supply air of the ventilation system. You can just see a schematic here. Okay, so what we did on these projects was install a cooling coil on the supply air ventilation system, and we also included a recirculation loop here, taking air from a circulation zone, a hallway, and recirculating this air in order to give the system more power. Despite doing that, you could see the monitoring results from before. We were way outside of the comfort zone that we wanted to be in. Conclusion. A cooling coil on the ventilation system alone in hot climates, depending on the house and its use, is generally going to be insufficient to deal with peak cooling loads. It can be really good for dealing with spring, autumn, and kind of in between months. And it's obviously it's a simple and relatively elegant solution, but it's not enough power. It's not enough cooling power, particularly in heat wave conditions. So if we look a little bit about at the PHPP, how does it calculate cooling loads? Okay, this is good to be clear, because otherwise, in our experience as well, we see misunderstandings and misinterpretations of what are those values that you see coming out of the PHPP on the results page or on the cooling load or heating load tabs. It's the average daily, if we're talking about cooling, sensible and latent cooling load. Okay, so that's the average over 24 hours of the peak sensible, which is temperature, and latent, which is humidity cooling load. Okay, so the fact already that it's an average 24-hour value is important to understand. The other thing that's important to understand is that it's an average across a whole building, so it's a watts per square meter. Now, if you have a west-facing bedroom or kitchen with lots of glazing, and particularly kitchens, which are high gain areas, if we're talking about a residential, a home, there can be a peak load in that zone, which when you average it across a building is not reflected in the average value. Okay, so the PHPP is a single zone model. We're modeling an entire building just as one thermal zone. Okay, so that's great because it's simple, and we can get really actually very good accuracy despite being a single zone model. But it's important to understand that an average across a building might not reveal differences in specific zones. Okay, and the boundary conditions for at least for small residential buildings when the PHPP calculates the cooling load is it takes the maximum daily outdoor air temperature, dew point, and solar radiation data. Okay, so again, that's a 24-hour average. The peak will be a lot higher than that. Okay, and it might be that peak that gives you 6 hours of really real discomfort in the building, and in which the cooling equipment needs to be able to get that heat out of the building. Standard occupancy, according to the PHPP for small residential, is if it's a 150 square meter home, it's going to calculate 3 people roughly. So if your client invites 10 people around for lunch on a Saturday in July, it's not 3 people, it's 10. So we just need to bear in mind that the standard occupancy is by no means a peak occupancy level. Internal heat gains will vary, but they will typically be in the range of about 3 to 4 watts per square meter. Okay, in a kitchen, you might have much higher internal heat gains, peak internal heat gains, which are generating a lot more heat. Particularly if people start making pizzas or baking things or using high gain equipment in there. And then shading devices. The PHPP calculates a reduction factor for the cooling load that actually assumes that people close the blinds more because it's too hot, and takes that into account for the cooling load. Okay, which is you could say a reasonable and logical assumption. But it's also possible that people don't drop the blinds. They forget to, or there's no control system that does it automatically, or simply they've been away for the weekend and they forgot to pull the blinds down, and they get back on a Sunday afternoon and the whole place is roasting. So it's important to understand what these kind of base boundary conditions are for the PHPP, because they may not correspond to, will often not correspond to what people will do in a home, and what you need to bear in mind when you're sizing the cooling plant. So if we then look at alternatives to using a PHPP, the kind of optimum tool would be something like a dynamic simulation tool, which is typically going to be a multi-zone tool that's going to use hourly outdoor climate and indoor set points and occupancy activity and equipment operation and so on. So these are going to be tools that are going to give us a time-dependent, high-resolution cooling load calculation, and above all, zone by zone. But the question is, do we need this level of accuracy for smaller residential buildings if we're doing passive house? Do we need this kind of accuracy for sizing cooling equipment, particularly given the time that it takes to input the data into the model, which we've already spent on the PHPP? So this is a kind of output that we'd get from our dynamic model. We'd have the design capacity per room. We would have the time at which that happens. We'd have the maximum operative temperature. All this really interesting data, which is great. But the question is, do we need that level of accuracy? Well, obviously, it depends a lot on the kind of building that we're talking about, the size of the building, the complexity of the building. This is a kind of crude example, but if we have this, like we see on this image on the left, this is a very small schoolroom. Single zone model is going to be pretty good here. If we've got this is on the right hand side, we can see an elderly people's residency of about 5,000 square meters. Clearly we're going to have very different conditions and heat gain situations in different parts of the building in that case. So we need to consider the size and the complexity of the building. We need to look at localized short-term climate conditions, especially solar gain, which facades might be receiving a lot more sun, which windows, which openings are going to get more punishment from the sun in the afternoon and so on. So we need to look at those issues. And of course, occupancy density and hourly schedule. What are people doing in the building? Is this residential? Of course, if it's a gym, we've got to take a completely different approach. If it's an office, we need to look at the how many people have we got in there generating how much heat at what time in the day. And then of course, what equipment's in there, when's it on, and how much heat is it going to add to the to the space. Of course, in multi-residential passive house, for example, recirculation circuits on that domestic hot water can be a real killer, because we've got this 60 degrees centigrade water recirculating around a building 24 hours a day, and that's a massive radiator heating up our building. So these are all the things we need to sort of take into account. Here's a quick example. This is just a very small single family home. It's a simple example just to try and keep it more simple, okay? But this is just an example of a comparison between the PHPP calculation and a dynamic simulation tool for calculating the cooling loads, okay? This is a house that we worked on, certified passive house in Mallorca in Spain, 170 square meters of treated floor area. And what I've done here is just present the PHPP, but with modified boundary conditions, and compared it to a dynamic simulation, right? To try and draw conclusions, is a PHPP going to give us a good level of accuracy? And what are the differences zone to zone, okay? First of all, let's look at the default cooling load climate boundary conditions for this project, okay? So this is the data that's just coming out of the PHPP that we've used for the certification, okay? What have we got? We've got an outdoor maximum temperature of either 27.4 or 27.2 degrees centigrade, okay? I don't have a automatic calculator for Fahrenheit there, but it's those are the conditions that it's calculating, okay? There's always two weather conditions for the cooling load and the heating load calculations in the PHPP, and then it takes the results from the worst, and then the dew point temperature is 21 to 21 degrees centigrade approximately, okay? So what does that give us? It gives us a cooling load of 8.7 watts per square meter sensible cooling load, and 2.7 latent, which is what you can see here. It's a total cooling load of 11.4 watts per square meter, okay? So the first mistake is to say, great, I'm going to use that, multiply it by my 170 square meters, and then I have the kilowatts that I need in order to tell the installer to put X kilowatts of heat pump in there for cooling, okay? Because these are obviously not peak conditions, climate conditions, and then also we'll look at occupancy conditions. Okay, these are the average over 24 hours. Okay, and that's an important distinction because you know, we've suffered the consequences of that. Okay, so if we look at the steps in terms of modifying the boundary conditions of the PHPP, these are the steps that we would recommend. Of course, there's others, and it'd be great to debate this, but this is what we've found to be a good kind of process over the course of these last years. Okay, so the first is to modify the climate file boundary conditions based on the analysis of the hottest day. So we look for hourly data of the hottest day in the location that we're designing for. You know, from a local Met station, and if not, with a tool like Meteornorm or similar, you know, which can generate statistical weather data. Ideally, try and find real data from a weather station in the last few years, because of course, you know, PHPP is also working on historic data from the last 10 or 20 years, and the last 10 or 20 years is nothing like what's going to happen over the next 10 or 20 years. You know, over the next 10 or 20 years, things are going to get much hotter. So so we look at that. So you can see here this example. Okay, here we're looking at the red line is the air temperature on the hottest day for this location, in this case in Mallorca, so reaching 38 degrees. We have the average, sorry, we have relative humidity here on the blue dotted line with the crosses, and then we have the dew point here on the green line. Okay, so we've got a minimum temperature of 24 degrees. That's hot. It's not getting cool in the night at all. You're not going to be able to do much at all with natural night ventilation. It doesn't matter how much inertia you put into the building. You know, really pretty high peak temperatures, 38 degrees centigrade. You know, so this is the evolution. We're looking at a photo of a day here. Okay, so of course the average temperature is going to be much lower, and that's what the PHPP is going to be looking at. But we want to look at the peak. Okay. You know, the average on that day is 31 degrees. Okay. When we look back to the PHP conditions, it was the default conditions. It was much lower. Okay. And the average dew point is 27 degrees. Okay. Again, much higher than what we had in the original climate file. So we go to the climate tab on our PHPP, and the great thing about the PHPP is it's kind of open source. You know, we've got all of these 30, 40 years of investigation, research by the PHI, putting into this tool, and we can see exactly what's in there and modify things. You know, so we can open up the cells on the climate tab and introduce our own climate data. You know, in the user option of putting in your climate data. Okay, so we can put in this data. We can put the 38 degrees maximum temperature. We can increase the dew point temperature. You can also modify the solar radiation data if we have it for our site. Okay, in this case, we've left it as is because it's gonna be relatively characteristic of a hot day. Okay, second step then is to look at the occupancy gains. So again, this is a question of the project in a specific project and knowing how the building is going to be used. In this case, we know that the client is going to invite people around for a lunch at a weekend, right? And there's going to be 10 people. Okay, so we increase the occupancy to 10 people and use user-determined occupancy level. Okay. Next, the cooling set point. Okay, and that's another thing you need to talk to the client about. Is, you know, what are the expectations here? What temperatures are people going to want? So here we talked to a client and that was 24 degrees. So we set that there. You can adjust that on your PHPP according to what you need. You know, so of course here 25 degrees is going to be the full value for certification, but you can adjust that. So in this case, we've adjusted it to 24. Okay. Step 4, the PHPP assumes that there's a soiling factor on the glazing. It assumes that the glazing is kind of dirty. Okay, so it takes 5% off the G solar factor, which of course, when it's a new building as well and everything's nice and clean, assuming that, you know, people have cleaned the windows a bit after finishing the build, you can just take that factor off. You know, so multiply your solar factor, your G value, by 1.05, just to eliminate that default soiling factor. Step 5, external shading devices. Now, this is always an issue of debate, but you need to, again, I think, talk to the client and evaluate. In our experiences, it can be risky to assume that people are going to use the blinds in an optimal way all the time. Unless you have a client that really says, look, I've got a control system, it's going to be controlled and I'm not worried about it. Okay. But generally, and in this example, what we do is assume that the blinds are not down. Okay. So we eliminate that temporary reduction factor for sun protection in the shading tab. Okay. What are the results? Now, if we compare the dynamic simulation model of this home to the PHPP, this is what we've got. Okay, so the correlation is excellent. There's a 1% difference in the cooling sensible cooling loads, 1% in the latent cooling load, basically very similar. So 6.4 kilowatts, 6.4 kilowatts between the dynamic and the PHPP model. Now, if we look on a zone by zone level, then we start to see that there are some differences. Okay, so if we apply that at 37.4 watts per square meter to each zone in the PHPP, these are the red bars here. Okay, if we look at the dynamic calculation, okay, how it varies from zone to zone, taking into account equipment gains and occupancy and solar radiation zone by zone, we can start to see a big difference. Okay. So this is a very small example, but if you extrapolate it to a larger building, then you can start to get problems. What we can see is that the peak cooling load for the kitchen, according to the dynamic model, is 37% higher than according to our PHPP. In the case of the toilet, it's 68% higher. Now, that's a very small space, and it's kind of distorted by applying a watts per square meter to a small space. Okay, but the point here is you've got a bit of a difference in the zone to zone levels. Okay, but for a single family home or smaller residential buildings, those differences will probably not be a big problem, as long as the distribution of the cooling system is adequately designed. Now we can do some sensitivity analysis. So looking at what happens if we assume that the blinds are down or not down. So here you can see on this table the assumption of no blinds, which is the results that we've seen in the previous slide. And then if we assume people are using the blinds properly, then the peak cooling load drops from 6.4 kilowatts to 5.6. 23%. So 23% sounds quite a lot, but actually it's a lot of very little. So the difference in costs between a heat pump of, let's say, 7 kilowatts and 5 kilowatts, at least here in Spain, is about 200 euros. It's just irrelevant, really, the difference in that power when you get that low. Okay, so my advice would be, don't put 5 kilowatts in, put 7 kilowatts in, and assume that people don't drop the blinds, because the capital cost of the system is not going to increase significantly in any way at all. The operating cost, the energy bill, is not going to increase significantly at all, because between a 7 kilowatt and a 5 kilowatt heat pump, it's going to be able to modulate down to about 30% of its nominal power. In which case, that means that the machine will be able to drop its power down when there's not a huge cooling load, and the energy bill is not going to be significantly higher. Okay, if we're talking 20 kilowatts to 7 kilowatts, of course, that's a major difference. And the rule of thumb, at least around here, if you talk to a lot of installers, is 100 watts per square meter. Most installers, if you talk to them and say, what size heat pump do I need here? They're like, 100 watts per square meter. Here's the quote. 100 watts per square meter would mean a 17 kilowatt heat pump for this house. Okay, and we don't really need more than 6.5. Okay. So that's always the ongoing debate and discussions and arguments that you may have or end up having with different people on site and off site. Anyway, the conclusion here is it's safer just to assume that people don't use the blinds in a perfect way. Okay. This is what this graph shows here. What this methodology, or this kind of this process that we've applied to 28 different passive house buildings here in Spain. And we can see the average is around 41, 40 watts per square meter. Okay, so the rule of thumb of 100 watts per square meter, we now, when we start a project, we just say 40. And that's what we start with before even calculating anything. So that's where we start as a ballpark figure with. And again, apologies for all of the Eurocentric metric units here. I can see that there's quite a few of you helping out here with translation. This is obviously much higher than that value that came out of our PHPP for the certification, which was 12 watts per square meter. Okay. So basic conclusion, just be careful when you see that 12 watts per square meter or 13 or 14 on your PHPP verification page. Don't use that to size cooling equipment unless you want uncomfortable phone calls while you're on the beach during a heat wave and when you're on holiday. So and then we compare that. This is just a brief comparison of looking at a larger building, and this is where we can see that the PHPP obviously has some limitations that we need to use different tools for. This is a large elderly people's residence in Spain, and here you can see the solar radiation analysis on the different facades. And here is a cooling load calculation for the dining hall. So here we have 27 people in 114 square meter space, average heat gains of 21 watts per square meter. Okay, so we had 7 watts per square meter in the previous example in our single family home. So here we've got a lot of people, elderly people, obviously not especially active. They're not all jumping around too much, but there's a lot of heat in there. There's equipment, there's heat, and there's sun coming in, even with blinds. So here we've got a peak cooling load of 157 watts per square meter. Okay, this is what we can see here on the blue lines, reading off the vertical axis on the right here. This is a peak cooling load, and here on the green line we have the indoor operative temperature and then the outdoor air temperature. So these obviously much higher peak loads. Doesn't mean we necessarily have to size the kit to absolutely meet that, but this is a larger building which has big differences in zone to zone. Okay, and of course this is a vulnerable collective. The elderly people, we can't have them overheating and as they're having lunch. Anyway, just an example of a multi-zone calculation for that zone. Of course, if we use the PHPP just to model this area, we would probably get the same results. We should get the same results if the boundary conditions are all correct. Okay. I mean, it's not rocket science. The calculation is fairly simple. So if we follow the same example of this elderly people's residency of a double bedroom, 2 people in 31 square meters, average heat gains of 7 watts per square meter, then we've got a peak cooling load of 47 watts per square meter. So that's kind of where we were on our average that we saw in the previous graph across all of those projects. So which would be more a kind of residential setting. So conclusions. If you generate a copy of your PHPP that you've used for design and certification, if you're certifying, then save a copy of it, adjust the boundary conditions, and if you follow some of the tips that we've shown here and others that you might consider relevant, then you can use it safely for sizing cooling equipment for smaller residential buildings. That's clear. For larger, more complex buildings, especially with high occupancy density and high gain areas, and then you're going to want a more detailed multi-zone and preferably hourly calculation, to make sure that you can meet the cooling loads at different points in the day in different areas. And of course, cooling distribution is just as important as sizing the kit. You've got to make sure you can get the heat out of all of the spaces adequately, not just the size of the equipment itself. And cooling coils on the ventilation supply air as the only cooling system can be very risky because it's just limited power. You need to look at the ventilation ductwork. If it's very small and compact and you have a small apartment where you don't have long duct runs, then you can be a little safer. But if you have single family homes with long duct runs, the temperature is going to rise as it goes through those ducts, and when it comes out of the valves in the room where you want to really cool, the temperature is not going to be sufficiently low. And of course, test your assumptions. Test it with your model. See what might happen in different circumstances. learn, of course, from completed buildings, which is where, as I said at the beginning, all of this came from. And above all, if you can, monitor them, because that really gives you totally invaluable information about how to assess real life performance. And I would add, talk to people, of course, after they've lived there for a while, because they're going to be the best people to give you feedback in terms of how well the building's performed and what's worked and what hasn't worked. So that's it, at least from the presentation. So we have a bit of time for questions, and
Fantastic.
I'm much looking forward to talking some of this and debating some of this through. So here you have my data anyway, if you want to get in touch, and Ken, please take us through.
Great presentation. Fascinating. And I think we've definitely got some good questions here to get to. I think I'm just curious a little bit to step back in the context of Passive House and its evolution, and your personal journey getting to this and really digging into it. Obviously, the heat waves are overwhelming us at times, but I find it interesting. Passive House coming from a cooler climate, air conditioning was somehow my characterization was cheating. That you're to do everything possible to never have to actively cool the building. And certainly in some climates, it's not possible. And as cooler climates are getting warmer, we're seeing that. And I'm wondering how you struggled, going from, aggressive passive strategies, which we need to maintain, to saying, hey, we need to be low energy cooling, and that's okay. Was it just having problems, or did you feel like?
Yeah, great question. It was all having problems. Yeah, it was all based on having problems. I mean, and particularly after a few of these, my response to clients was, okay, if you don't want to do this, then please just send me an email in writing saying that you don't want to put active cooling in, and that you can't then come and complain to me, because obviously we have, there's media articles and stuff that come out, saying Passive House, you don't need anything, you don't need any heating or any cooling, which is great for selling stuff in a way, but it's obviously completely false advertising, because you do need something,
Right.
So we'd have clients that say, oh, it's okay, we'll be fine in the summer, it's a passive house and we'll just ventilate, So if you open the window and it's 38 degrees outside, you're ventilating with 38-degree, air. So this is what happened on a few projects, and I just resent the mail saying, okay, we discussed this, and you agreed that this was your decision and this is what's happened. So I did try to warn you, So yeah, that's definitely an issue. I mean, I think the main argument, the main reasoning or explanation we try and give to our clients is, you're going to have a passive house. It's going to be awesome. It's going to be a great building. It's going to be super comfortable. Okay. And you're going to use very little energy to keep it warm in the winter and very little to keep it cool in the summer. But in all coastal, particularly coastal, warm, humid climates, you're going to need some active cooling. Okay. But it's not going to be cooling like a jet of freezing air shooting down your neck as you're watching telly in the sitting room in the summer. It's just going to be a small airflow, which is just taking heat out of the home, and it's you're not going to hear much, because the split units or the fan coils can run at lower flow rates and so on. So all of these things are what we try and explain to people. In some cases, people are quite clear, because here in Spain, air conditioning is not new at all. Of course, it's people, you can't get by without it in a lot of places.
Right.
But that's definitely an issue. Yeah.
Yeah, absolutely. So on the climate inputs in the PHPP and the data that you're using, are you doing any variance for future climate, or are you taking basically the data, the extremes that you're seeing today, and like how are you navigating that?
Yeah, good question. I mean, what we're generally doing is taking recent data and not applying any percentile reduction on that data. So you don't want to oversize things, but I mean, if we try and take data for a really hot day, the hottest day in the last 4 or 5 years, and without applying any percentile reduction of that data, then we're generally fairly confident that that's going to be sufficient to deal with the next 10, 20 years. So the danger, of course, is then really oversizing equipment, and then
Right.
you're kind of going over the top. Ultimately, most people, I think, and then most of our clients, if it's a major heat wave and it's 26 degrees centigrade in their home at 55% relative humidity, they're not going to pick up the phone. They're going to be okay. The issue is just making sure temperatures don't get really, really much too high. So that's what we generally try and do, is look at a recent 2-3 years
Hmm.
hottest day and look at that data
Right.
with with that example that I gave in the Mallorca house.
So in terms of the data that you're seeing and monitoring, you mentioned at the end, what are you able to do more monitoring? Is it
Yes, I mean, never as much as we'd like. Monitoring is I think it's probably the thing that gets me most excited about all of this, but it's time consuming, expensive. The equipment has a cost, and then the hours of analysis has another cost, which most of the time there isn't money for. I mean, I
right?
think what's really needed here is a sort of university-led public funding and research that should look at passive house heat summer conditions in a large range of buildings to really draw conclusions. And I think that's has happened in some cases, but that's, I think, what's really needed, because particularly not just to measure temperature conditions, but to measure peak cooling loads, which again is not that simple, because it depends on the cooling equipment. If it's a hydronic water cooling system, then it's easy to do. If it's a refrigerant distribution system, it's not that easy to do.
Mhm.
But I mean, we haven't been able to monitor peak cooling loads in our buildings. We have been able to monitor temperature and humidity conditions. Yeah.
Right.
Hmm.
Well, it's good to have. There was a question early on, distinction technical, where you had kind of juxtaposed the idea of using air temperature in place of operative temperature.
Yes. Yeah.
I
No, I saw.
hear that right? And what,
Yeah.
yeah, could you explain a little bit more?
Sure. Yeah. No, I saw that question. That was a great question. No, the issue was simply that what I was presenting on the graph was measured air temperature, not operative temperature. Just because measuring operative temperature is complicated, because you have to measure the mean radiant temperature. So you have to have a spherical radiant temperature sensor, and then an air temperature sensor, and you would need to do that in every room. So the point was just to not create confusion, because the PHPP is operative temperature, but what I was presenting on the graph was air temperature, which is generally what's going to be the cheapest and simplest thing to measure. So it was just that difference. Yeah.
That's interesting. Very good.
Because you could be measuring, for example, air temperature in a radiant. You've got a radiant floor for cooling, and if you measure the air temperature, that's not the comfort temperature, because if the floor is at 19 degrees and the air is at 28, your operative temperature may be in that room, well, add them together and divide them by 2, it may be 24. So
Mhm.
so just to understand that distinction, when you're measuring air temperatures, you're not getting the whole picture. So that was just the comment there.
Yeah, I have to say, I've never heard that brought up before.
Mm,
Where it makes total sense in terms of the combination of the different factors,
mm.
and then doing the shortcut. When you are looking at dynamic models, do you have a recommendation? What do you like to use?
I mean, we use Energy Plus with the design builder front end. So that's the dynamic tool that we use. Of course, there's lots around. IES in the UK is quite common, I think, and then TAS and various different ones. But yeah, we use Energy Plus with a design builder front end, which is a good manageable way of dealing with some of the complexities of
Yeah,
programming Energy Plus yourself. So that's the tool we use. Yeah.
great. So at the example, if I heard this correctly, you did take a look at the multifamily building with some room by room occupancies using the PHPP and getting values that were pretty good in terms of comparing it to the dynamic model.
Hmm.
You still would be very reluctant to actually do a whole building that way. Or
Yeah. I mean, it's a question of practicalities, and of course there's fees and people are paying you for a certain amount of hours, and you there's a practicality issue. I mean, we doing a PHPP model for every room in a multi-residential building would be just completely impractical, so
well, the
ultimately.
extremes, right? Those corners and the
Exactly. You could do the extremes, and that would be a kind of a more efficient way of doing it for sure. I mean, generally, what we do is if we've been contracted by the client to do some thermodynamic modeling, then which we often are in terms of looking at overheating, then we have the dynamic model up and running. But the idea is always to try and make use of the PHPP if it's been put together, and make use of that, because you got to keep a lid on the hours that are going into this, and try and make use of what's gone in there. But yeah, the results are similar because if the boundary conditions are similar, then any simulation tool is going to give you the quality of data based on what you've put into it, and
yeah, no, excellent point. And so in terms of the boundary conditions, are you ever looking at them as variants within the same model, or is that just locked
in a thermodynamic model, you mean?
in the PHPP?
Oh, well, of course, the PHPP would be, it's a photo, it's a static calculation, but you can of course adjust that. You could say, well, if there's more people, what happens? Just adjust the occupancy level, and you can take different photos by adjusting those boundary conditions. Yeah, absolutely. I mean, you can open up cells that are locked and adjust them too. For example, if we use the PHPP for heating loads, then we unlock the internal heat gains and put it at 0, because it assumes that there's always a minimum amount of heat gain in a building. So, you can tweak pretty much what you want in terms of the PHPP. That's why it's such a great tool. Partly because it's relatively simple to use compared to thermodynamic modeling. It's got a really spectacularly reasonable cost for the amount of work you can do with it, in terms of modeling. And it's you can tweak it, you can work with it and do some kind of sensitivity analysis. So, that's great.
Yeah. But so to change hats a little bit, if you, as a building certifier and you're looking at somebody's PHPP, how are you digging in to these sorts of issues?
Yeah, well, that's a good
Any
question.
modifications to the PHPP?
Absolutely, that's a good question. Because you're kind of like there's a certification criteria, and then there's what you probably think is very likely to happen. Most of the time, those are absolutely aligned, but sometimes they're not, because there's every model makes assumptions, and every model is wrong. It just some of them are useful. That famous quote. For example, to give you a concrete example, we're certifying currently a 5,000 square meter multi-residential building in Andorra, in the Pyrenees, not too far from here. Okay, so the overall, this is a 16-story building. So the overheating, there's no active cooling planned. Okay, the overheating in frequency for the whole building is 1%. Okay, so the client said, that's great, it's all going to be fine. Of course, we look into that, and now the great thing on the passive cooling tab, you've got an analysis already built in into what happens if people don't use the blinds properly, if there's no natural ventilation, if internal heat gains are high, and of course, even on that graph, you can start to see that you're getting up to 15%. So there's various things there. If you're not using active cooling, the passive cooling overheating frequency is obviously a whole building value. So that doesn't mean that on the top floor of a multi-residential building, people might be at 29 degrees in the model, and in the bottom floor, they might be at 22 degrees. But because the single zone model is averaging all the data, you're not seeing that with just one single value. No. So what we've done in that project is talk them through that graph, which is a really good update for PHPP, and talked about some of the practicalities of what this might imply. and have made a recommendation to them to include active cooling, which has been completely ignored. But you know, because their argument is nobody, even in high-end flats here, puts active cooling in. Okay, so fine.
Right. Today, right?
Today, exactly. But what we've agreed with the client is that there will be a laminated guide on by the front door of each house saying this is what you need to do in the summer in terms of using the blinds and ventilating, and ensure that at handover on the purchase of the apartments, people have a manual explaining this, and that at least there's this communication takes place as when the apartments are handed over to the people who buy it, so that they're aware of it. And there's another issue here, which is kind of backdrop to the whole thing, is in our experience, expectations are always really high in a passive house. People expect it to be awesome, which is great.
Right.
And there's another little anecdote which I think is always interesting, is that we also have people who complain that their fridge makes more noise in their passive house than it did before. which is funny, but it's relevant because the fridge made the same noise in their previous house that it does in the passive house. Because in the passive house it's so quiet, the acoustic comfort is so fantastic. You can hear everything more, So they start saying the fridge is making more noise, and the same happens with temperatures. People start to get more sensitive, I think, to these things. So the expectations are high, and we need to build that in. Of course, I think the best passive houses are the ones with really active users. That's the bottom line. But you can't always assume that everybody's going to be totally on top of these things.
Yeah, no, absolutely. So we're we're at time, but I thought I'd throw out one more question here on that we have regarding thermal mass. And have you looked at thermal mass and turn those dials? And what do you see? What do you think?
Yeah, great question. Thermal mass it becomes a kind of religious debate, at least in my experience here, because there's a kind of, you either believe in thermal mass or you don't, and it's kind of like, I mean, the dynamic simulation that we've done, and lots of other people have done it, and Passive Institute, Dr. Jürgen Schneiders has done it in his study of, Mediterranean passive houses. A bit of thermal inertia is useful, but it's only going to be useful if you have low temperatures in the nighttime and you can have natural ventilation, which is taking the heat out of that mass. Thermal mass on its own obviously doesn't do anything. In a passive house building, thermal mass has less of an influence than in a non-passive house building. Because once you have good thermal insulation, good air tightness, good windows, and good shading devices, the mass kind of gets a bit bored and doesn't really do all that much. So it's an issue. I mean, we have clients, there's a lot of lightweight timber construction. We say, where could we get a bit of inertia in the building, and we try and recommend that. But we have experience of passively cooled, very lightweight buildings here in heat waves, and they've been fine. People just have to be more careful with the shading and the blinds and stuff. So my conclusion is always is that really, thermal inertia is good, but its impact is going to be less in a passive house building, and it's only going to really be useful if you've got low nighttime temperatures and you can have nighttime ventilation.
And in the heat wave, you're not necessarily going to have that.
Exactly. You saw that data on the graph there. The minimum temperature on that hot day in Mallorca was 24 degrees. When we have heat waves here in Barcelona, it doesn't get below 26 degrees sometimes in the night. So it doesn't matter how much you ventilate. You're only going to add more heat to the building, even at 5 in the morning when the temperature's at the lowest, So yeah, thermal inertia in that sense kind of just flies out the window. And in fact, there's an interesting example of a project in Dubai, which they built with lightweight timber. This is an office in Dubai where it's sort of 45 degrees outside most of the time, because thermal inertia doesn't have any effect there. Because the temperature is just always so high. You've got, in fact, it's probably counterproductive because the mass will absorb heat and then it will just keep radiating heat to the people on the inside. So that was a kind of interesting, more extreme example. So yeah, thermal inertia is good. I think you just need to look at it in each context and not kind of overestimate its importance in a passive house building.
Yeah, terrific. Well, this is fascinating. What a great dive into these issues and coming at it from different directions and into the PHPP and the depth of it is really fantastic.
Great. Well, it's been a pleasure, and I hope it's been interesting to all of you. And I hope we can all see each other in person at some point in a future conference. And best of luck on all your projects. And I hope people don't overheat.
Yeah, absolutely. And please, everyone, consider Oliver is in Spain, but he's, one of these global Passive House leaders. And it's one of the things we really appreciate about Passive House is the international and global knowledge network sharing. So thank you again, Oliver. Thank you everyone for coming. And I look forward to being in touch.
Great. Thank you all.
Have a good evening.
Thanks again. Bye.
Have
Bye-bye.
a good afternoon, everybody. Bye-bye.